So recognize that many gas samples are not pure, but are mixtures of gases. Air, for example, is a mixture containing nitrogen, oxygen, argon, carbon dioxide, and a few other gases in trace amounts. Mixtures of gases are everywhere. You're swimming through one right now. Now, in certain applications, you can think of the mixture as just one gas. So, for example, even though air is a mixture, we can measure the pressure, the volume, and the temperature of air as if it were a pure gas, if it were a pure substance. And we can then calculate the number of moles of molecules in an air sample, knowing pressure, volume, and temperature, even though they're different molecules. So let's take a look at this thrilling simulation one more time. Let's say I were to put 50 molecules of this heavy species, this purple gas, into the container. Note that the pressure is about 0.2, 0.3 atmospheres. If I add an equal amount of a different gas, notice that the pressure roughly doubles. Half of that pressure is coming from the purple gas, the other half is coming from the red gas.
Good day. So now we're going to cover the last gas law, which is pressure versus moles. It works the same way as all the others. So we have a relationship between pressure and number of moles that is a direct relationship or proportional. P over N is always constant, which means that we can say P1 over N1 is equal to P2 over N2. And as usual, if I increase the pressure by a certain factor, that has to be related to the number of moles increasing by the same factor. Normally we're going to look at it the other way. So we're going to say, for example, if we double the number of moles, well, the pressure should probably increase by a factor of 2 as well. So if we look at the graph, because we have a direct relationship, a proportional relationship, we get a straight line. Again, it ends up at the origin. Why? Because if there are no moles of matter, if there is no matter, there are no collisions, and therefore there cannot be pressure, since we know that pressure is exerted by collisions from the gas, between the gas particles and the walls of a container, for example. So no matter, no collisions, no pressure. So we have the line ending up at or starting at the origin of the graph. We have a car tire that is suitably inflated, contains approximately 5 mole of air at a pressure of 220 kilopascal. How many moles of air remain inside the tire when it has partially deflated and the pressure indicated on a manometer is 185 kilopascal? So what we're going to do here, So we're going to use, of course, P1 over N1 is equal to P2 over N2. So if we replace, P1 is 220 kilopascal, N1 is 5.0 mole, and on the other side we have 185 kilopascal, and we're looking for the number of moles that it corresponds to. So we're going to cross multiply to find the value of N, and the value of N is, value of N is 4.2 mole. So that's it for this gas law.
Dalton's law is probably the most obvious law. So, a lot of times in real life, we're not dealing with a pure sample. And so, we've talked about this previously in the year. That with solids, like we have metal alloys, and those are mixtures of metals that are bonded together. And so, a lot of times we have these mixtures of things. Well, the same thing happens in gases. So, for example, the air around us that we breathe, the air around us is a mixture of different types of gases. We obviously breathe in the oxygen, right? And we use the oxygen, but we're really breathing in all of the mixture, and our body is just pulling out the oxygen gas and doing a exchange and then releasing CO2 gas. So the mixtures should make sense that if I have a mixture of different gases, right, then they should all add up together. So Dalton's law became a law for a very funny, obvious, like, I mean, he made one of the most obvious things, like notices. And that was that if you take like individual pressures within a sample of gas, the total pressure of your gas is basically the addition or the sum of all the individual pressures of each gas in the mixture, right? So it should make sense. So if I have a tank of air, right? Really, all the parts have their own individual pressures. So in air, we have lots of different gases, but let's say we have oxygen, like in this example. We've got oxygen gas, nitrogen gas, argon, water, CO2, right, to make our air. Well, all of those gases in a sample contribute to the total air pressure that we're putting in there, the total gas pressure that you're like pumping into your tire, right? Or whatever it is. So they just add up. So it's fairly easy. So the key is they all have to be at the same temperature, volume, and the moles have to, like, closed container. Well, that's going to happen because of the fact that, it's a sample or a mixture. The amount of pressure that a single gas in a mixture contributes is called the partial pressure. So that's what we're referring to when we say partial pressure, is the individual pressure that a single gas is contributing, right? And that's what this little capital P is. And then we write a little subscript down here at the bottom for whichever one it is. So that tells us which gas is which. So otherwise, it's a fairly easy, straightforward, like, concept, or the formula you can see is pretty straightforward. So in this scenario, it says air contains oxygen, nitrogen, carbon dioxide, and some other trace amounts of gases. What is the partial pressure of the oxygen? So see how we wrote the big P? Normally that O2 would be little. It just isn't on this document. And it's the partial pressure of oxygen, and we want to know at a total pressure of 101.325. If the partial pressures of nitrogen, carbon dioxide, and other gases are, when it says respectively, it means they're in the same order. So what that means is my P total equals pressure of nitrogen plus pressure of CO2 plus pressure of other, right, is what we're going to write there because it's others, and pressure of O2, which is what we're looking for because that's what we wanted. So we know that all those have to add up. Well, we're told the total pressure is 101.325 kPas. That's going to equal, and then all of the other ones are also in kPas, which is nice. If they're not, you have to convert them into the same unit. So then, respectively, the first one was 79.10. That was my nitrogen, kPas, plus the pressure of O2 is the next one. That was 0.040 kPas. Plus the third one was the other, which is 0.94 kPas. And the pressure of O2, which we do not know. So all we're really doing in this scenario is solving for pressure of oxygen. So that should be pretty easy. So we're going to add up the 79.10, 0.040, and then 0.94. Remember when you add and subtract for sig figs, you keep the fewest number of decimal places, so we're just going to keep 2 decimal places. So I'm going to add these up, right? And so basically that's going to be 80.08 kPas plus the pressure of O2 equals 101.325 kPas. And then, so then from there you're subtracting, right? Minus 80.08 kPa. I left my unit off there, sorry. So that we can isolate the pressure of O2. So when we solve that, again, we want to keep the fewest number of decimal places. So we're going to keep 2 decimal places. So when I solve that out, it's going to be 21.245. So we're going to actually drop off the 5, but it's going to actually round it up. So it would be 21.25 kPas equals the pressure of the O2.